Welcome everyone to just 1 minute. Okay, it's recording. Alright. Okay. Welcome everyone to week 2 of the PMRF TA sessions for the NPTEL course Electronic Properties of the Materials, Computational Approach. A brief introduction of mine. I am Akshay. I am a PhD student PMRF in the Soil State and Structure Chemistry Unit SSCU of the Indian Institute of Science, IISc Bangalore, India. I did my BTech MTech dual degree from IIT Kanpur in the Department of Material Science and Engineering, and I am an NPTEL PMRF TA for this course. So we will have total 8 2-hour interactive problem solving sessions every Friday from 7 p.m. to 9 p.m. during the run of this course, and this is the second session. Unfortunately, because some technical issue, I had to postpone this session, which it was supposed to happen on 1st September from 6 p.m. to 8 p.m. From 7 p.m. to 9 p.m. But unfortunately, due to some technical issue, I had to postpone it, and now this session is happening today on 3rd of September from 6 p.m. to 8 p.m. But in general, these sessions will be on every Friday from 7 p.m. to 9 p.m. Alright, so a brief intro. So what we are going to do in this session. So first of all, we will complete our problem from week 1 session. So in week 1 we started with problem number, we did a problem number, in problem number 5 we did a problem on the Drude's model from Ashcroft and Mermin. So we will start with that problem. So we completed part A and B of that problem. Now we will complete the rest of the part C, D and E. Then after completing that problem, we will solve some problems on stationary states and infinite square well from Griffith's Introduction to Quantum Mechanics by David J. Griffiths. And then after solving those problems, we will look into the infinite square well problem in case for a symmetric potential. So in case when our infinite square well is instead of having our infinite square well from 0 to a, we have our infinite square well from minus a by 2 to a by 2. So it's a symmetric potential. And then we will also look into a Python script which is similar to what we have done for the your general other infinite square well when you take from 0 to a, but there will be some changes. So we will see both from theory and code what are the changes, and in the end there will be 2 more problems then that I will just introduce, and you can try them on your own. And in case if they are if you find any issue with solving them, then then you can ask me on the discussion forum of the course, and then I can either help you out there, or if you insist, then we can solve those 2 problems in the next session as well. Alright, so let us start with today's session, and let us start with problem number 1. Alright, let me just 1 minute, let me just check if everything is recording. It's recording. Alright, so let's start. Sorry about it. Okay, so let's start with problem number 1. So we have solved part A and part B in week 1 problem number 5. So you can look into that video recording of that week 1 session for the part A and part B. Now we are going to solve part C. Alright, so let me just take this. So in part C, so the question, let's just go through it again. So in the Drude model, we know the probability of an electron suffering a collision in any infinitesimal time interval dt, that is given to us. It is dt by tau, and then it has asked several problems to us. In the first problem, we have shown that an electron picked at random at a given moment had no collision during the preceding t seconds. So let me just revise what we got from part A and part B. So in part A, what we had done is that show that an electron picked at random at a given moment had no collision during the preceding t second with probability e to the power minus t by tau, and show that it will have no collision during the next t second with the same probability. So basically, from part A, so what are the things basically we have is from part A and B. All right. Okay. So let just so first of all, what is given to us? So from the start, it is given to us according to Drude model. What you have is the probability of an electron suffering a collision in any infinitesimal interval dt is, so that is given by dt by tau, where tau is our relaxation time. So this is what is given in the problem. Then so from here we can derive, and what we did in the last session, we can just derive the probability of an electron suffering no collision. All right. So there will be no collision. The probability for that will be now 1 minus dt by tau. So dt by tau is that the probability that the collision will happen in time to dt, and thus the probability that electron will not suffer any collision, that is just 1 minus dt by tau. Now from part A, which was written, okay, so I just read it out. Okay, you can read it again. Like show that we have to, that if we picked an electron, then during that the probability that it had no collision during the preceding t second, that is probability e to the power minus t by tau. So basically that is what we proved in our part A. So for part A, what we have got is the probability that when an electron is picked at random, it did not suffer any collision during the preceding let me just check if someone is okay. So any collision during the preceding t seconds is, so this is the probability that we got from part A. Pt is equals to e to the power minus t by tau. So by this probability, the electron doesn't suffer a collision in the preceding t seconds. And from part B, which you can see, which is like show that the probability that the time interval between two successive collision of an electron falls in the range between t and t plus dt. So the time interval that is between two successive collision that falls between time t and t plus dt, that should be given by this probability that we had shown. So from there, basically what we got is this. We got p of t. So this is you can see this is small pt, and then we solved for or you can say the probability that an electron picked at random does not collide in interval 0 to t, and then thus collide in interval dt. So that probability is given by p of t is equals to e to the power minus t by tau dt by tau. Alright, so this is what we got from part A and part B. Now we are going to solve part C, D and E. Alright, so part C is show as a consequence of A that, okay, so we have to use whatever we got in A. So that's why I just repeated what we got from A and B. I just wrote the results. So now what we have to do in part C is that show as a consequence of A that at any moment the mean time back to the last collision or up to the next collision averaged over all electrons, that is going to be tau. Okay, so it means that at any moment, if we take the mean time back to the last collision, if we take the time which is back to the last collision or up to the next collision at any time that we pick, and if we take the average of that time, then that would average over all, and if we average that time over all electrons, that should be tau. Okay, so that we have to say that we have to show. So okay, let's do it. So the mean time back to the collision or up to next collision can be averaged over all the electrons as, so we have to take this average, so then we average over all the electrons as, that will be given by 1 by tau integration from 0 to infinity t times pt dt. Alright, where this tau is the time interval between the electrons, between the electron collision, which is basically our relaxation time. Just the definition of relaxation time, it is the time interval between the electron collision, so that we take as tau. And pt, now here this pt, what is our pt? Pt we are taking from our part A, from A. Okay, so from A, our small p of t from part A, so that we are getting from part A. Okay, so from part A we know that what is pt. Pt is the probability that an electron is picked at random and it did not suffer a collision from in the preceding t seconds. Okay, that is our pt. So p small t from A we can take it to be e to the power minus t by tau. So again, so we just have to substitute it here. So our average of average time, this mean time will be 1 by tau integration from 0 to infinity t times e to the power minus t by tau dt. Now to do this integration, what we can do is let x is equals to minus t by tau. Alright, so that gives us just one minute. Let's get back to it. Alright, so our t will be is equals to minus tau ln of, okay, so let me, so not minus t by tau, I am taking it as e to the power minus t by tau. Yeah, okay, yeah, so we can take x equals to solve this integration, we can take x equals to e to the power minus t by tau, and thus I can write t is equals to minus tau times ln of x, and then just take a differentiation, minus t is equal to minus tau by x dx. Alright, alright, so we have this. So using this, our integration, so our average time t will be written as 1 by tau, then at t equals to this t equals to 0, our x will be equals to 1. So we are doing the change of variable in integration. Okay, so you might know this. Okay, So we are just doing a change of variable. So at t equals to 0 our x will be 1, and at t equals to infinity our x will be 0, it is e to the power minus infinity, it will be 0. And then instead of t I can write this minus tau ln x, alright, and then e to the power minus t tau could be written as x, and then instead of dt I can write minus tau by x dx, alright. So alright, so now what we will have, this tau's will cancel out, and what will minus will cancel out, and what we will have tau integration from 1 to 0 ln x dx, alright. Now to do this integration of ln of x, we use integration by parts. So using integration by parts, alright, and the formula, let me just write the formula here. So like integration by parts is, if you have some u dv, so you just write uv, okay, you just do an integration of 1, and then what you do is dub and then dub, alright. So alright, so this is the integration by parts formula. This is I guess you guys you might already know, like this is basic mathematics. Integration u dv is equals to, you can write as uv minus integration duv, alright. So here we are going to do the same thing. Here we are going to take as our this v part, we are going dv we are going to take as 1. So integrating 1 over x will be x, it will be ln x from 1 to 0, right? Okay, and then we have minus integration, our v is now x, alright, v is x, and then du will be 1 by x dx from 1 to 0, alright. So this is easy, and let me just write it like this so that things are much more clear. Alright, so this value at x at 0 it will be 0, at ln1 is also 0, so this will just give you 0, so this will go to 0, alright. And this thing, okay, this will be equals to x, so what we will have will be x from and this will be a negative, so negative can flip the sign of the integration, so I can get it, I will get the range of integration from 0 to 1, and thus that will just give you tau, okay. So what we have obtained is, so our answer is, so what we are getting is tau is equals to, this mean time is equals to tau. That means I can write, therefore the mean time back to the last collision or up to the next collision averaged over all electrons is tau, alright. So this we have proved, that is tau. Okay, so this is our part C, that is done. Let's go to part D. Okay, so what is part D? Now in part D what we have to do is show as a consequence of B that the mean time between successive collision of an electron, that is tau. Okay, so mean time between two collisions, that we have to show that into successive collision, that is going tau using our B, and from B what we have is that an electron picked at random does not collide in the interval 0 to t but does collide in the interval dt, that is provided by our B part, alright. So that is given to us in B, and now we have to use that to solve the B part, alright. So solutions, okay, now so let Tc be the collision, be the time between, okay, be the time between two successive collisions. Okay, so let's say TC is the time between two successive collisions. Now, so the collision must occur. Okay, so if this is the time, then the collision must occur at TC plus TT. Alright, where dt is an, let me just put, I guess maybe I can just put this here, and this is okay, so the collision must occur at TC plus TT where dt is an infinitesimal, as we know, infinitesimal time interval alright. Now from B, what we have is the probability that an electron collision occur after TC is given by P of TC is equals to e to the power minus TC by tau dt by tau. Alright, now from here the probability distribution function for TC is given by, I will write it as rho of TC e to the power minus TC by tau. Alright, because that is the probability, and now from there, if we have the probability, we can get, from here we can get the probability distribution like this. Alright, then this implies the mean time between successive collision of an electron, so that will be given by, we have to find average of TC. So the average formula is, you just have to integrate, TC is positive, so from 0 to infinity, TC times rho of TC TTC. Alright, so that is the formula for an average. So you just take the value times the relative distribution, and then you just integrate it. Alright, and that comes 0 to infinity TC e to the power minus TC by tau. Okay, rho TC e to the power minus TC by tau divided by tau TTC. Okay, and as you will see, it is same as solved in part C. So what we find that if we get this integration, so you can see that it is the same integration that we solved here. So here also the average integration was from 0 to infinity t to the power minus t by tau by capital tau by tau dt, and here also we have the same integration. We have 0 to infinity tc e to the power minus tc by tau dtc. It is just the change in variable. So instead of t, we will now have our variable of integration is tc instead of t. So that's the same. So the answer got it. Okay, so that is the basically same integration, and so okay, so the answer is going to be the same. So this average TC is basically going to be tau. Alright, so this is what we have to do. Let me just write it in some different color. Let's take this. Average TC is equals to be tau. Okay, so that is the mean time between successive collision of an electron. Mean time between successive collision collision of an electron. Alright, okay, so now let's quickly go to the last part E. So what is part E? Okay, now again I guess this question is quite lengthy. Part E is part C implies that at any moment the time t between the last and the next collision averaged over all electrons is 2 tau. Explain why this is not inconsistent with the resultant t. Okay, through explanation should include a derivation of the priority distribution function for this capital T, which is the at any moment time, which is the time t between the last and the next collision. A failure to appreciate this subtlety that Drude of the conductivity issue. Okay, only half of this. So this you can check out from the Ashcroft-Mermin book. So for part E, where it is already 6:26. So again I am getting into time constraint because of this issue, this problem. So let me just go through this quickly. Alright, just completed once. Okay, so the mean time back to the last collision averaged over all electrons is tau. Therefore, the mean time between the last and next collision average over all electrons is 2 tau. However, from the result of part D, one can see that the average time between successive collision collisions is tau. Now this is a paradox that can be resolved by considering the timeline of the single electron shown below. Alright, so if we see the trace timeline, let's say this axis, okay, let me just show it. This is let's say this is our timeline, this is our timeline T. Alright, and these are our collisions. Let's say two consecutive collisions are here, two consecutive collisions are here, and this. Okay, so these are collisions. Okay, so let me just write that thing. Now it can be seen from the timeline above that when the electrons collide too often, and are separated by large time intervals. Okay, and are separated by large time over the timeline. Picking a particular point on the timeline is likely to land on a large time interval. This will moderate the average time the average time interval to be larger than tau. Alright. So now, so this is the paradox, but we can understand that from this, like if the collisions are happening over a large interval within the timeline, then it may happen that we will land on something at some point where this although the collisions have more if we see the mean the successive collision, the time is t is tau, but on an average scale, if our collisions are happening at a larger time between a larger time interval, then let's say we can collide, we can come here or something, right? So in that case, this average time will be larger than tau. So here we are talking about capital T. So this is the average value that we have found. So the time between the last and next collision. So it seems like this time in between the last and the next collision, if we go to this big timeline, it may become larger than tau, which contradicts our which contradicts the what we got in part C. So now what we are going to do, we are going to find this average of this capital T. First we find its probability distribution, then we will find its average value, and we will use here the results from part C to show that it is consistent with part C. Alright. Now probability distribution for capital T can be calculated by using the property of convolution over the the contradiction was in terms of the contradiction is with part B. Sorry, yeah, what we got in part D said that between the mean time between the successive collision is tau. So that was part D, and now we are finding that because of this timeline issue that we have seen, it would be more than tau. From part C, it seems like it is going to be 2 tau, and we are going to take result from D to show that that is consistent, so that there is no paradox, which we can see from this timeline as well. Okay, so we'll take the result from part D and prove that average, what is the average of this capital T, time between the last and the next convolution. So probability distribution for capital T can be calculated using the property of convolution over the probability distribution. So this is probability distribution Pt equals to e to the power minus t by tau divided by tau, This is this as we have used it earlier in, okay, we have used this earlier in part D. Okay, so this priority distribution e to minus t by tau capital tau, as you know. For TC, this is the priority distribution we use for TC. So this is the result from D. So let me just write it here. This is result from D. Okay, so this is the result from D. So we are going to use this this convolution over this probability distribution over the interval 0 to capital T. Alright, now that will be given by what I will have is, now I want to find the probability distribution for this capital T. This is the probability distribution for capital T, which we have to find, times dt, that value is equals to from 0 to t. I can write it as this small pt1 dt1 times p of capital T minus t1. So you can Google about what convolution of probability is, and you will understand it much better. So I'm not going to go into the detail of what convolution probability is. You can check it out from some probability textbook. Probability and statistics textbook. Sorry. So pt by dt is equals to from 0 to capital T. This will be e to the minus t1 by tau dt1, and then we will have e to the minus capital T minus t1 by tau, and here we have dt. Okay, and t1 is from 0 to capital T. So what we have is p of t dt. Distribution of capital T, right? And pt dt, that will be equals to, I can take out this capital dt by tau square will be taken out. We will have 0 to capital T, e to the power minus this will cancel out, and we will have e to the minus t by tau and dt1. So this is very easy to integrate. We will have e to the power minus t by capital T by tau square dt, and this is just integration from 0 to t, that will just give you t. So I will just write the answer d dt. Alright, so from here, this is our pt dt. So from here our so pt dt is given by this, okay, so this is what we have achieved. This is what we know now. Now to find the average of capital T, that will be just from 0 to infinity, as we found for small tc. This priority distribution, so priority distribution will be this, okay, and integration over dt. Okay, we have to do t pt dt. All right, so that will be equals to from 0 to infinity. This will be t square e to the power minus t by capital T by tau, where by tau square dt. Alright, now here it will be the same technique as we have used. So yeah, we have to take like x equals e to the power minus t by tau. I will take the change of variables same. So let x is equals to e to the power minus t by tau minus capital T by tau, from where we will get t is equals to minus tau ln of x, and we get dt could be written as minus tau by x dx. Alright, so using this, if we do the integration, so since we are getting out of time, and so I'm just gonna give you the final result. So basically what you will be left with after doing some integration. You have to do some you have to check it out, but this will come as ln of x whole square dx. And then similarly, use integration by parts. Use integration by parts. Alright, again let me just write the formula. U dv is equals to ub minus integration v du. Alright, just use this property, and what you will found is that this average of capital T will be is equals to 2 times of tau. So here using the part D, we have seen that it is 2 tau, and that is what you will get from part C as well. So let me just write it down quickly. Therefore, one can see that average of the distribution is indeed equal to 2 tau, which is in accordance so okay, let me just write this as average of tau equals to 2 tau. It is what we will get. It is in accordance with what one would predict using the result of C. Alright, so we use result of part D to get to this average, and we found that this average is equals to 2 tau. That is what we will get from part C. Alright, so that contradiction, that paradox is solved now. Alright, so we are running out of time. So problem is a long problem. So okay, let us try to cover up. Alright, so let us now start from this problem number 2. Problem number 2. The rest of the problem, they are going to be from Griffith's Introduction to Quantum Mechanics. So now it is problem number 2. Suppose a particle starts out in a linear combination of just two stationary states. Psi x is just c1 times psi1 of x and c2 times psi2 of x. Okay, assume that a constant cn and a state psi n are real. Okay, what is the wave function psi x comma d at subsequent times, and find the probability density and describe its motion. So it is easy. So the first part is very easy. First we have to just find psi x comma t. So we know that okay, there is it is a linear combination of two stationary state. So there are so we know that then we know that we can write psi x comma t as just combination for stationary state. They are time dependent part will just be written as psi1 of x, and it will be e to the power minus iota e1 t by h cross, and I can just say c2 psi2 of x e to the power minus iota e2 t by h cross. Okay, so where we know that where okay, so psi x comma t will just be written as c1 times psi1 of x, and we will have time dependent part from e to the minus iota e1 t by h cross, and for psi2 also e to the minus iota e2 t by h cross, where e1 and e2 are the energies associated energy eigenvalues. Let me just say it is, these are the energy eigenvalues associated with psi1 and psi2. So now next part is that okay, so this is just the psi x comma t, easy. And now we have to find the probability density, and we have to describe its motion. So the probability density, that is given by psi of x comma t, it will just mean mod of psi x comma t whole square. So that is given by complex psi of this star is the complex conjugate. Alright, so basically if you have a plus iota b, okay, so this wave function, so psi 1 psi 2 are real, but as you can see it is e to the power iota, so that is a complex term. That brings so this becomes a complex number, and conjugate, just a division of if you doesn't remember, a plus ib, sorry, if a plus iota b, that is our complex number, and if we take the conjugate, okay, just write it properly. If I take the conjugate, if you take the conjugate, that is just a minus iota. Alright, so let's get to it. So what I will have is, and I will represent it by a star on it on psi, so psi star x comma t times psi of x comma t. So that will give us c1 times psi 1, so c1 are real and psi 1s are real. So if you take the complex conjugate of them, they will not change, but now there will be a change of in front of iota, minus iota will become plus iota. We will have iota e1 t by h cross plus c2 psi 2. Okay, initially let's say this is what you will have. So we will have a complex conjugate of all of this. Alright, I am not writing this x, psi 1x, psi 2x now. Just write it properly. Now this will be complex conjugate of this will be e1 t by h cross plus c2 star psi 2 star e to the power minus iota e2 plus iota e2 t by h cross. Okay, I have taken the complex conjugate of everything. Alright, and then we know that c1 and psi 1 are real. We can assume that cns and sins are real. So I can just remove this star sign, because they are real. So their complex conjugate will be the same. C1, and we have C1 psi 1 e to the power minus iota e1 t by h cross plus C2 psi 2 e to the power minus iota e2 t by h cross. Alright, then we can do the multiplication here, and what we will get C1 square psi 1 square plus C2 square psi 2 square, plus we will have a cross term C1 C2 psi 1 psi 2, we will have cross terms where common we will take out this, and what we have is e to the power minus iota e2 minus e1 t by h cross, plus which is basically multiply this and this and this 2's, okay, multiplying this and this and this, multiplying this and this. Alright, so multiplying this and this, multiplying this and this, c1 c2. Okay, so we will have this common iota e2 minus e1 t by h cross, and we have e to the power iota e2 minus e1 t by h cross. Alright, and this I can write as c1 square psi 1 square plus c2 square psi 2 square plus 2 times c1 c2 psi 1 psi 2, and we will have a cos. So you just have to use e to the power iota theta. Let me just write it here. Okay, use e to the power iota theta is equals to cos theta plus iota sin theta. So this is what I have used here. So that gives us cos of e2 minus e1 t by h cross. Okay, cosine of this. So I can write here conclusion. The probability density oscillates sinusoidally at an angular frequency minus E1 by H cross. Now this is certainly not a stationary state. Okay, so it is changing with time, so the product density is now changing with time, so this psi x comma t is not a stationary state, and it is the product distribution, it oscillates sinusoidally, not a stationary state. Alright. But there is something we can note is that note that it took a linear combination of states with different energies to produce motion. Alright, so this we have to take into note, because this cosine function, it has E2 minus E1, so if E2 is equals to E1, then this cosine function will be 0, and then this psi x comma t will also be stationary state. So basically this two states should not be degenerate. So if we do a linear combination of the degenerate states, which will have the same energy eigenvalue, with degenerate state they have the same energy eigenvalue, so in that case our E1 will be equals to E2, and then the psi x comma t that will also be a stationary state. So this we have to take a note. Now let's go to problem number 3. So problem number 3 is, okay, we have to prove the alright, sorry about that. So let us start with problem number 3. So in problem number 3, what we have to prove these 3 theorems. So first is that for normalization solution, the separation constant E must be real. Okay, so what it is saying is that so basically let me just go to the solutions. Okay, so for part A, basically what is asking is that, okay, we have psi x comma t, we define psi x comma t stationary state as psi of some psi at x comma 0 times e to the power minus iota e t by h cross, and here it is asking us to prove that this E has to be real for this psi x comma t to be normalizable. So this E has to be real. So to prove it, we will prove it by contradiction. So that E is equals to E naught plus iota times gamma. Okay, so that E is equals to E plus E naught iota, where E naught and this the gamma are real. Right. So now psi x comma t could be written as psi x comma 0 times e to the power minus iota instead of e plus iota gamma t by h cross. So now this could be written as psi x comma 0 e to the power minus iota e naught t by h cross, and then we will have iota square plus gamma t by h cross. Alright. Now psi x comma t mod of psi x comma t whole square, probability distribution, probability density, that is given by usually I'm using this as maybe this is capital X psi x comma 0, and this denoting it as mod of psi square, and e to the power minus iota plus iota, that will just give us 1, and what we will have is 2 to the power iota gamma t by h cross. Alright. Now okay, and so now for it to be normalizable, what we want is that mod of psi x comma t whole square dx, that has to be equals to 1. Alright, so from here we have minus infinity to infinity mod of psi square e to the power 2 iota gamma t by h cross dx, that has to be equals to 1. Okay, this is not 2 iota, there is no iota. Okay, it will be equal to e power 2 gamma t e to the power 2 gamma t by h cross, and e to the power 2 gamma t by h cross, e to the 2 gamma t by h cross, 2 gamma t by h cross dx. That has to be equals to 1. We can take the e to the power 2 gamma t by h cross common here outside the integration, and mod of psi square dx, that has to be equals to 1. Now what we can see is that the second term is independent of t time t, correct? So if the product is to be 1, this is basically two terms. This is our one term and this will be our second term, and what we are saying is that product of these two terms is there has to be equals to 1 for the normalization. And what you can see that the second term, which is this term, the second term is independent of time t. So if the product is to be 1 for all time t, the first term, let me just show you the red colors. So that is t, so this is the first term and that's the second term, okay, underlined by green. The second term, the first term is the red one. The first term, okay, must also be constant. Constant with respect to t. This gamma should be equal to 0. Okay, because the first term e to the power 2 t by tau, 2 after t by tau, that 2 gamma t by h cross, that has to also be constant with respect to t. So hence this gamma has to be equal to 0. Then it will be a constant all times t. Okay, and therefore we can see that therefore t is real. Okay, this being proved. Alright, so this is a part A. Let's go to part B. So in part B, what we have to prove is the time independent wave function psi x can always be taken to be a real, unlike psi x comma t, which is necessarily complex. Okay, so we can so we have to prove that. So most of the time in the different square we have seen that this psi function it was real, but now we have to prove that we can always take this psi x to be real, and you can read rest of the part afterwards. Okay, so let's just go to this solution of part B. Part B. So if psi satisfies time independent Schrodinger equation, TISC, that is time independent Schrodinger equation, alright, and TISC, that is psi minus h pi square by 2n d square by d square d square by dx square plus v or x psi is p of psi equals to e of psi. So our psi, if our wave function psi, it satisfies this TISC. Okay, taking the complex conjugate, okay, it satisfies this equation. This is now taking the complex conjugate obtain that V and E are real, we can note that V and E are real, what we can get is minus h square by 2m del square psi star by del x square. So you can write D because we are considering psi to be a function of x only. So V of psi star, that will be equal to E times psi star. You can write del or you can write D. Equals to E times of psi star. Okay, so here V and E are real. We are considering V and E to be real, and that you can see from this part as well. Like it has given you a hint how to solve this problem. So V and E are real here. So where we can see that from 1. So let's say this is equation number 1. Now from 1, psi star also satisfies TISC, which is a time independent Schrodinger equation, and then any linear combination of psi and psi star will also satisfy the time TISC time. Okay, so if both psi and psi star they satisfy time independent Schrodinger, so any of their linear combination will also satisfy this TISC. So let me just prove that. So let me just prove it for a general case. So basically, if let's say psi 1 and psi 2, let's say we have a psi 3 which is C1 psi 1 plus C2 psi 2, where psi 1 and psi 2 satisfies TISC, and let's say with same energy eigenvalue. Okay, so these I am the energy eigenvalues. I am taking this to be degenerate states. They have the same energy eigenvalue because we are in our problem we are solving for psi and psi star, and you can see that E is same for both psi and psi star. So energy eigenvalue is same. So if we have psi 3, which is a linear combination of this, then what we can see that if we put psi 3 in our time dependent Schrodinger equation, psi 3 does psi x square plus V times psi 3, then what we can see that we can minus h phi square by 2m. I will have del square del x square C1 psi 1 plus C2 psi 2, right, plus V times C1 psi 1 plus C2 psi 2, right. This gives us C1 times minus h phi square by 2m del square psi 1 by del x square plus V times psi 1 plus C2 times minus h phi square by 2m del square psi 2 by del x square plus V of psi 2. Now since psi 1 and psi 2 satisfy this TISC, time independent Schrodinger equation, but we will have some energy eigenvalue E times psi 1, and both are degenerate, so they both have the same energy eigenvalue. Let's say E. So we will have this. Now I can take E common from here, and what we have is C1 psi 1 plus C2 psi 2, which is basically is equals to psi 3. So this gives us E times psi 3. Okay, so this is how we have hence psi 3, or let's say like therefore psi 3 also satisfies TISC. Right, so this is the proof that the linear combination of the psi 1 psi 2, which both satisfy TISC and have the same energy eigenvalue, then psi 3 will also satisfy TISC. Alright. Okay, now so now we can say that from this general solution we can say that this is also true that since psi and psi star both are satisfying TISC, so they any of their linear combination will is also going to satisfy TISC. Now back to our problem. Then thus psi plus psi star, which is one linear combination, and iota times psi minus psi star. Now here both of which are real, also satisfy TISC. So here I'm not going to prove this thing, so you can check it on your own. Check it. Okay, that both of these also satisfy TISC. But we can say that in general we have shown that if psi and psi 2 are there, they both satisfy they both satisfy TISC. Then any of their linear combination will also satisfy. So now we have taken linear combination such that both the linear combination are real, and from above we can say that okay, they will satisfy, and you can check them as well. You can just put psi plus psi star into the TISC, and then you can check if they satisfy this or not. Alright, so now and they are real also, you can check that they are real as well, that you can also check. So from here let us go to the conclusion. So what we have conclusion. From any complex solution we can always construct two real solutions. Of course, if psi is always real, the second one. So basically you can actually check that psi plus psi star, even if psi is complex, then psi plus psi star and iota times psi minus psi star, they will be real. Okay, so you can check that as well. Okay, using just take the complex conjugate of this, and you can show that they are real. So basically you can check that psi plus psi star, if I take the complex conjugate, if I take psi 1 is equals to psi 1 plus psi star, okay, then psi 1 conjugate, you can take this conjugate, you can take the conjugate of this, which will be psi plus psi star O star, and you can find that that is going to be equal to psi 1, and then same you have to take for this iota times psi plus psi star. Okay, I'm not doing that right now. So okay, so that we can prove like this. Now of course if psi is always here, the second one will be 0. So second solution that we have written, so we have proved that from any psi we can get two real solutions, as we have seen here, both are real, and you can prove it here, or you can check they will satisfy as we have proved here, and you can check that they are real as well. So, and also if psi is real, then psi is equals to psi star, and psi second one will be 0 only. So in particular since this psi is equals to half of psi plus psi star minus iota times iota psi minus psi star, psi can be expressed So even if psi is complex, we can express it as a linear combination of two real solutions. Okay, and okay, so we can always express psi as a linear combination of two real solutions, and similarly, if you can, so both of these will also be a solution of psi, as you can check. Okay, so as we have proved, okay, so this psi 3 they are also a solution of this, and thus we can take this solution of time dependent Schrodinger equation, we can just take these solutions to be real. Okay, because we can always even if it is imaginary, we can always do some linear combination of it and get the real solutions, as we have done here, and vice versa. All right. Okay, now the C part is, if Vx is an even function, that is v of minus x equals to Vx, then psi x can always be taken to be either even or odd. Okay, so this is what we have to prove, that the wave function psi x will be either even or odd. Right, so let's do part C. If our Vx is an even function, so this so if psi of x satisfy TISC, which is minus h square by 2m del square psi by del x square plus v times psi, then changing variables x to minus x and noting that del square by del of minus x whole square is equals to del square by del x square minus hy square by 2m del square psi of minus x by del x square plus v times of minus x times psi of minus x, that could be written as e of psi of minus x. Now if v of minus x is equals to vx, okay, so it is an even function, then psi x us, then okay, now if v of x is equals to v of minus x, then what we will have is minus hy square by 2m del square psi of minus x by del x square plus we will just v of x psi of x is equal to e times psi of minus x e times psi of minus x. So therefore psi of minus x also, we have this, so therefore psi of minus x also satisfies TISC. Alright. Now since psi x and psi minus x both satisfy TISC, then consider psi plus of x, that will be equals to psi of x plus psi of minus x, which will be an even solution. So we can check that here, we can check that psi plus of minus x will be equals to psi of minus x plus psi of x, which will be equals to psi plus of x. Okay, so this is an even solution, and we will consider psi of minus x, that will be equals to psi of x plus minus psi of minus x, which will be an odd solution, which we can check that psi of minus x, that will be equals to psi minus x minus psi x, will be equals to minus of psi of negative of this function. Alright, okay, you can check, you can see this is just the negative sign. Alright, here, so now we can write, so let me just write conclusion, or let me just write this, here, both psi plus of x and psi minus satisfies the TISC since they are linear combinations of psi x and psi of minus x, both of which satisfies TISC. But psi x could also be written as half of psi plus of x plus psi minus of x, this you can check. So any solution can be expressed as a linear combination of even and odd solution. Alright, so that's why about our if our Vx is symmetric, then the solution size will be either even or odd, because we can always get this linear combinations. Right. And let's go to problem number 4. Right behind. Right. So now problem number 4 is, okay, show that E must exceed the minimum value of V of x for every normalizable solution to the time independent for the time independent solution TISC. What is the classical analog to this statement? Okay. So this we have to prove that, okay, so for this time independent solution equation, to get a normalizable solution, we need this that our energy E must exceed the minimum value of whatever our V of x is going to be. So this we have to prove, and the hint is also provided here. Let's do it now. Given, okay. So given, what we are given is del square psi by del x square is equals to 2m h by square times V of x minus E times psi. Okay, this is what we are given today. Now if E is less than V min, then let's see, this I will represent as psi double prime, and this is psi only. Okay, so then psi double prime and psi always have the same sign. Okay, so they are going to always have the same sign, because as we can see, this will be positive if E is less than V min. So if E is less than V min, then this term is always going to be positive. The both side double prime and psi, they are going to have the same sign. This means psi always curves away from the axis. So basically what we have, if I plot psi as a function of x, if you plot it as a function of x, then what you will get is that if psi is positive, then what you will have is that this will go like this, because psi double prime, that also has to be always positive, and if psi is negative, then you will get this kind of curve, because psi double prime, it always has to be negative. So here psi is positive, So the psi double prime also has to be positive, and if psi is negative, then the psi double prime it also has to be negative, because we are considering that if E is less than V min. Now for a normalizable, solution, psi should go to 0 as x tends to minus infinity. Okay, so if our psi function is, let's say our psi function, we are defining it for all the x values. Okay, yeah, we have some vx, we don't know, but whatever our vx is, the psi has to go to 0 as x tends to minus infinity. Now at some point t, at some point it it has so it's got to it has to go it has to got to depart from 0. Okay, if it doesn't, it's going to be 0 to be identically 0, going to be identically everywhere. In say the positive direction. So basically what we are saying here is that let's for the normalization, our wave function which comes from here, okay, let's say our wave function is coming from here, so it will be 0 for x tends to infinity. At minus infinity it will be 0. Okay, our function will be psi of x has to be equals to 0. At infinity my psi of x will be 0. Okay, now it will be 0, let's say it could be 0 everywhere. Okay, it could be 0 in a whole negative, that's fine, but now it has to become positive somewhere. Okay, it has to become somewhere, let's say even if it is 0 for x less than 0, it is x to 0. If it is 0 everywhere, but it has to rise up now. It has to rise, it has to become non-zero, and since our psi x this psi it could not have psi prime to be 0, like it has to be a continuous function. So it need to be a continuous function, so it will rise up. And here you can see that what is going to happen is that if it rises up in some positive x greater than 0, then what is going to happen is its curvature, the psi double prime will now here at this point, the psi double prime will be less than 0. Okay, I should have written it in this direction. So if psi is greater than 0, then we have psi double prime is also greater than 0, and if psi is less than 0, then psi double prime is also less than 0. Okay, but if we start from psi minus infinity, then it has to rise up. Okay, and if we are talking about psi is positive, then in that case it has to rise up, and if it rises up at any t, even at minus t or something, at minus x or something, at any x, it has to rise up. But if it rises up, then psi double prime is now becoming 0, is now becoming less than 0, which contradicts our fact that if E is less than V min, then psi double prime has to be greater than 0 if psi is greater than 0. So that contradicts our fact. Okay, so that is the contradiction that we are getting. Now at this point, its slope is positive, and increasing, so psi gets bigger and bigger as x increases. Okay, sorry, this okay, sorry, my mistake. So sorry about this. Okay, so side over prime here, so it is not written this as okay, sorry. So what will happen is that, okay, now if we start increasing it, so it is 0 at x tend to minus infinity. Now if it has to become non-zero at some point, and the condition is that side over prime has to be greater than 0. So side over prime will be greater than 0 here. So for this will just keep increasing. Okay, so this function now it will just keep increasing. So let me just draw it somewhere, not on x greater than 0. Let's say at any point, like you can have at x equal to 0, you can have it at anywhere. Okay, and just put this somewhere else. Let's say this is our psi of x, this is of 0. So at any point, if it has to rise, then it will start rising. Let's say at any some positive value or anywhere you can say. But if it start rising, then what will happen, that we need side over prime to be greater than 0, then it will just keep increasing. So now would not be 0 at x tends to infinity. Okay, so similar condition what we have for x equals to minus infinity, we need the same psi x condition for normalization x tends to infinity. But since we need the, if psi function is positive, we need this side over prime to be greater than 0. So it will just keep increasing. But if it keep increasing, if we have some different this kind of curve is going, if it's going to be, sorry, if it increases and it starts increasing or something, then what will happen is that it could not be 0 at x tends to infinity. Alright, so that is the contradiction that we have. So it could not be normalized. Okay, now I'm just gonna write it out. The psi gets bigger and bigger as increases. Okay, so let us put it at x greater than 0 for safety. It just keeps increasing. Right, increases. Now it can't ever turn over and head back towards the axis because that would require a negative second derivative, or let's say negative side over prime. Now it always has to bend away from the axis. As we have seen here, it always has to bend away from the axis if E is less than B min. By the same token, if it starts out heading negative, it just runs more this runs more this it just runs more and negative, runs more and more negative. And And similarly, if it goes into the negative direction, so if it becomes negative, and so even if it becomes negative, so then it will still goes into this direction. It will always goes away from this axis. Okay, and you can just go from the plus infinity as well. In neither case, is there any way for it to come back to 0 as it must at x tend to infinity in order to be normalized. Okay, so in order to be normalizable, alright, so that's why our e could not be less than the b min, because in that case our function could not be normalized. It will always go away from the axis, and if you go from minus infinity, it can even if it goes side positive or negative, it can never go back to 0 at x infinity, which we also needed for normalization. Alright, so we are already okay, so we only have about 30 minutes now. So let me just do a few questions, and then we will go to infinite square wave first, symmetric potential first. Alright, so let's so this is from Griffiths. Okay, this problem is from Griffiths. Let's see, okay, so this problem we have from Griffiths. So let's say we have a particle in the infinite square wave which has the initial wave function is given as ax times a minus x for x between 0 to a, 0 to small a. Now for some constant capital A. Now the function is also given here. Now outside the wave, of course, we are taking psi to be 0. We have to find psi x comma t. So we will solve this problem 5 and problem 6. Both are related to each other. So we just solve this for 5 and 6, and then we will go back to first to our infinite square wave symmetric potential. Alright. So in this part, what we have to do is find psi x comma t. Okay, we have to find this psi x comma t function. So first we need to normalize the function. Okay, first normalize psi x, normalize psi x comma 0, which is given to us to determine capital A. Right, so we will have minus infinity to infinity mod of psi x comma 0 whole square dx. It has to be equals to 1, and here we have minus infinity. We will have from 0 to a, 0 to a only we have function defined. We have a square x square a minus x whole square dx equals to 1. Right, so I will not do the integration, but basically, okay, so this is the integration that we have to do. We have to do x square times a minus x whole square dx equals to 1. So because of time constraint, I am not gonna solve this integration. Okay, and this is a simple integration. Actually, you just have to open it and just do the integration. So what you will get is we have a square times a to the power 5 divided by 30 equals to 1. So from here we will get our e equals to the root square root of a to the power 5. So this is our capital A. Right. Now to find psi x comma t, psi as a function x comma t, first we need to first we need to find So first we have to write this wave function as a linear combination of let's say, since it seems similar to particle in a box, so we go from 0 to 8, so we can write it as a linear combination of the solution of a particle in a box. And then going from that, if we know the cn's, then going from that psi x comma 0 to psi x comma t, that will be that, as we have done earlier in our problem number 2 as well, then that we can do easily. Okay, so what we will do, so what we will do is, we can write this psi x comma 0 x summation of n cn psi n of x comma 0, where this psi n's, where these are where these psi n's, psi n of x comma 0, I will just write it as psi n, where this psi n's, these are the eigenvalue eigenvector, these are the eigenvectors for particle in a box problem. Alright, so this we know. So we know psi n of x, we know psi n of x. So just 1 minute. Alright, already it is 1:26 minutes. Okay, basically, okay, yeah, so we can write this psi x comma 0 as cn times psi n, which are the eigenvectors for a particle in a box. And we know that this psi n will be equal to the root of 2 by a sine n pi x by a. Alright, this we know. So I can write this psi x comma 0 now as this summation of n cn psi n of x. So, and this will be equal to, what we are saying is that this is going to be equal to ax times a minus x, where we have find this a is equals to under root of 30 divided by e to the power 5. This is according to okay, now we know that we can find the cn by 0, from 0 to a we have to do this, because then we are aware of coefficient defined psi n of x psi of x comma 0 dx. Okay, so this is the formula that we are going to use to find our cn's. So here cn will be equal to integration from 0 to a under root 2 by a sine of n pi x by a times psi of x comma 0 dx. Okay, so and psi of x comma 0 also we know psi of x comma 0 is our it will be this constant a times x times a minus x dx. So this is the integration that we have to do. Alright, and so I'm not going to do the integration because of constraint of time. I'm not going to do this integration. So this you can integrate, and if there is any issue with the integration problems, then please let me know. I will provide the solution in the discussion forum of the course. If you have any question, you can ask in the next session as well. Alright, so you can do this calculation, this simple integration. Use the integration by parts formula. You have to use integration by parts formula. Let me just give you one hint how to solve it. Okay, let me just do one more step, just a single step. So basically, take this root 2 by a out, and just take out the constant. So the constants will be equals to 2 under root 50, okay, using the value of a that we have found, okay, under root 30 by e to the power 5. We will have this here a cube now, and then what we will have is, we will have this a times integration from 0 to a x times sine of n pi x by a
dx and minus integration from 0 to a x square sine of n pi x by a dx. Okay, so we have to do this two integration. This is let's say I1 and this will be I2, and so you can make this question into instead of this one integration, basically you have to solve this two small integration and use integration by parts. So let's get it with red. Solve for I1 and I2 using integration by parts. Okay, again a reminder what integration by parts is. U dv could be written as uv minus integration v d. Alright, and if you solve it, then your I1 will come as minus a square upon n pi cos of n pi. Okay, and your I2 will come as I2 will be complicated. It will be minus a cube upon n pi cos of n pi, okay, plus 2a cube upon n pi whole cube cos of n pi minus 1. Right? So you just solve it and you will get minus a cube upon n pi cos n pi plus 2a cube upon n pi cos n pi minus 1, and I1 will be minus a square upon n pi cos n pi, and you can see that is a times, so these two terms will get cancelled out when you put I1 and I2 for the Cn, and after putting these values you can check that your Cn will be equals to 4 under root of 15 upon n pi whole cube 1 minus cos of n pi. Okay, so this will be our Cn. Okay, so basically Cn is coming as, it will be 0 if n is odd, because if n is odd, that cos n pi will be if n is even, if n is even, so if it is even, then cos n pi will be 1, 1 minus 1 will be 0, so our Cn is 0, and it is 8 under root of 15 by n pi whole cube if n is odd. If n is odd and cos n pi will be minus 1, it will be 1 minus cos n pi will give us 2, and thus we will get a non-zero Cn. Alright, so from here we have our psi of x comma t. Now we can write as summation over we know it will be, we can write it as psi of summation of Cn sin e to the power minus iota E n t by h cross, where our En will be is equals to n square pi square h pi square by 2n t square. So our psi x comma t can be written as, because we have the same summation of n equal 1, 3, 5 and so on, because for even n's it will be 0, 8 to the root of 15 upon pi whole cube root 2 by a sine of n by x by a e to the power minus iota n square pi square h pi square by 2n t square. Okay, here we have e and t by h cross, so there will be a t by h cross here. Correct? Yes. So this will be our final answer. Okay. Alright, so this is how we find our psi x comma t, and that is what we have to do in this problem. Now let's go to problem number 6. 3. Which time do we have now? Okay, we have only 16 minutes. Okay, let's quickly solve this problem number 6. So now in problem number 6, now we have to prove the following relations for a wave function which is provided as a linear combination of an eigenstate of a knot solution. So we are using this thing, so now we are just gonna prove this theorem quickly. Okay, so in the first thing we have to prove it. Okay, so let's see. Okay, so basically given that we have, let's say, a psi of x comma 0, we are saying that we can write it as some cn psi n. The eigenstate could be written as a linear combination of some eigenstates of a known solution. We can write our wave function as we have done in problem number 5. And now we have to prove these two relations regarding this. So first thing we have to prove it. To prove, let me just write it down. We have to prove summation of n equal 1 to infinity mod of cn whole square, that is equals to 1. This is what we have to prove. So how we are going to prove it? First we will do the normalization of this our wave function psi x comma 0. So for that we have infinity mod of psi x comma 0, that has to be dx that should be equals to 1. Now this I can write as psi star complex conjugate psi x comma 0 times psi of x comma 0 dx, that has to be equals to 1. Then we will use the definition of psi x comma 0, which is summation over say m equals to 1 to infinity cm times psi. Okay, our sign is given as summation of n equal 1 to infinity. Okay, so this is given to us. This is given. So let me just write it here and write that this is given to us. And now we will use that thing. So psi m star times summation of n equal 1 to infinity cn psi n dx, that has to be equals to 1. So we can take the summation out. We have summation of m equal 1 to infinity and we have summation of n equal 1 to infinity. We have cm star cn and we have integration sin star psi n dx, that is equals to 1. Now since psi n are science are orthonormal, that is, so what we have is minus infinity this psi n star psi n dx. So that will be equals to this delta mn, where delta mn is chronicle delta. Okay, here this is called chronicle delta, and the property of chronicle delta is that this delta mn, that will be equals to 0, m not equals to n, and it will be equals to 1 but n equals to n. Alright, because sin and sin are orthonormal, so it will be equal to chronicle delta. And chronicle delta is this, it is 0 for n and n is equals to 1 for n equals to n. So this implies we will have summation of n equal 1 to infinity, summation of n equal 1 to infinity cm star cn, and the integration will be equal to delta mn. Now that has to be equals to 1. For delta mn will be equals to 1 for cm equals to cn. So we have summation of n equals to 1 to infinity now. Cn star cn will be equals to 1, which implies basically means summation of n equal 1 to infinity mod of cn square, that will be equal to. So here we have to. Now second part that we have to prove. Okay, so this is the first part we have proved. This is n equal to infinity mod of cn equals to this, and the second part that we have to prove. We have to prove this, that expectation value of our Hamiltonian, this is the average energy, that comes as summation n equal 1 to infinity mod of cn square here. This we have used, but now basically we have to prove this simple this thing. For this, okay, now we know that h cap of psi n is equals to En times psi n, alright, and what this expectation value of h cap, so we have our, it will be with respect to our wave function, this psi star x comma 0 h cap psi of x comma 0 dx, it means this, and the integration I am not writing it, but basically it is minus between infinity. Alright, now we can write our wave function again as m equals to 1 to infinity cm psi m star cm psi m, this will be complex conjugate of this h cap, and n equals to 1 to infinity cn psi m, and we will have a dx. Alright, now again I can take out the summation outside, m equals to 1 to infinity summation of m equal to 1 to infinity cm star cn integration let's not put the limits. The limits are from minus to infinity, it is obvious. I will write it as psi m star h cap psi n dx. Now we know that this h cap acting on psi n will give us En times psi n, okay, this we know, okay, this we know. So we have summation of m equal 1 to infinity summation of n equal 1 to infinity cm star cn integration sin star cn times psi n dx, okay, using this thing, okay, using this we can get this, right? Now again, so now we have m equals to 1 to infinity summation of n equal 1 to infinity cm star cn times en integration from psi m star sin dx, again this will be equals to Kronecker delta. So we have m equal 1 to infinity summation of n equal 1 to infinity cn star cn en, and it will be derivative of mn. So from here we can see that, so our average hk will be equal to summation of n equal 1 to infinity, because of Kronecker delta we will have mod of cn square times en. And we prove this second variation. Alright, now let's go to the part B. The part B of the problem is, for the wave function of problem number 5, okay, determine the coefficient of which eigenstate of the particle in a box dominates, and also determine that coefficient value. Find the expectation value of energy of the wave function and compare it to that of the energy eigenvalues obtained for a particle in a box problem. Okay, so basically we need to determine the coefficient of the eigenstate of which eigenstate of particle in a box that dominates, because the Cns basically gives you the how much are the Cns in that wave function psi x comma 0. So we have to find whichever of the Cns are the maximum for our wave function of problem number 5, and then we have to also find the expectation value of energy that okay, from this formula we will use of this wave function and compare it to the energy eigenvalues obtained for a particle in a box problem. Alright, so let's go to part number B. Now here, just by looking, if you just look at problem number 5, so the wave function, so for problem number 5, the wave function looks like this, which is similar, so it is from 0 to 8, it doesn't have any node, which gives us an idea that okay, it looks more similar to our ground state. So so one thing you can do is you can take the function of Cn and maybe you can do the differentiation and find that for whatever the Cn value function for Cn that we get for in the problem number 5, you can differentiate it with respect to n and find for whichever n value the Cn is maximum, or we can just do some smart work and we can see that our wave function doesn't have any node. So it seems like it is the dominant one is going to be the ground state of our particle in a box case, because for the particle ground state of the particle in a box case as well, for n equals to 1 also there is no node. So that's why we can just find the C1, and if C1 is very large, then we can just get our answer. So that's what we are going to do instead of doing the differentiation for the function of C1. Now the wave function in problem number 5 closely resemble the ground state psi 1 is for n equals to 1 This suggests that mod of C1 square should dominate, and in fact if you do mod of C1 square, then from the formula what you will get is 8 under root of 15 upon pi whole cube to whole square, and what you will get is that is going to be 0.998555 and so on. So it is almost 99.8555%. You can see that it is the wave function is made up of our ground state only, so clearly it is the dominant one. The rest of the coefficients make up the difference. The rest of the coefficients, they will make up the difference, right? And okay, and one can check that if you do summation n equal 1 to infinity for mod of C n square, so you can even check that this is going to be, as we have proved that this summation will be equals to 1, so you can check that whole square summation of n equal 1, 3, 5 and so on up to infinity, or 1 upon n to the power 6. So that will come, and this summation, basically this summation, this is a series summation, this comes as pi to the power 6 divided by 960, and this will also 8 into 15 whole square will also be 960. So what you will get, that this value comes as 1, and this will be pi cube, so pi to the power 6, both of them we cancel out, and it will be equals to 1. So the rest of the coefficient will be just 1 minus this, which is going to be very small value. So so dominantly our function is made up of our ground state of the particle in a box only. Now the expectation value of energy. Now since it is mostly made up of ground state energy, then we expect our energy also to be very close to the ground state energy. Expectation value of energy to be very close to the ground state energy of particle in a box. So expectation value of h cap, we will use the formula that we have just derived, which is summation of n mod of Cn square times En. Okay, we have derived this formula, and from here we can get n equals to again 1, 3, 5 and so on up to infinity. We have 8 under root of 15 divided by pi whole cube whole square 1 by n to the power 6 n square pi square h pi square by 2 me square. Alright, now what we will get here is, it will be 960, this 8 under root 15 whole square pi to the power 6, other constant will be pi square h pi square by 2 me square, and then we will have summation of n equal to 1, 3, 5 and so on up to infinity 1 upon n to the power 4. Okay, and square this, and this summation, this comes as pi to the power 4 by 960, and thus what we have is that our expectation value of h energy, it comes as 5 times of h pi square by 2 me square. So it is we know that for the ground state it is pi square h pi square by 2 me square, so it is close to that, but it is slightly higher only because there is an admixture of the highest state as well within our wave function. Now for particle in a box, let us just write it down. For particle in a box, ground state energy is for n equals to 1, that is given as E1 is given by pi square h pi square by 2 me square. So this expectation value of energy is very close to E1 although it is slightly larger, larger because of the admixture of the excited states. Alright, because since we have mixed some excited state to our ground state, so it is a little higher. Alright, so that is done. Problem number 6. Now we will skip problem number 7 and 8 for now. And how much time do we have left with? Okay, so actually we are almost over. It is 2 hours already gone. Alright, so we have just solved some problems. So for infinite square well, let me just quickly go through. Okay, I guess I sometimes just extend it to 15 minutes and just go through this problem quickly. So for the infinite square well symmetric potential, so the potential is basically this is like this. The potential of the infinite square well now will be Vx equals to 0 for mod of x less than a by 2, and it will be equals to infinity for mod of x greater than a by 2. Okay, so instead of being our potential from instead of having our potential from 0 to a, now we have our potential from minus a by 2 to a by 2. So if we do this solution for the TISC time independent Schrodinger equation solution, then it will be minus h square by 2m del square psi x by del x square plus Vx psi x equals to E psi x. Then we will have the boundary conditions. Okay, so I guess in this tutorial, yeah, I will just go through this theory part of this because we are already off our time limit. It's already more than 2 hours, so I will just go through the theory, and then the coding part we can and I will just show you the script, and maybe in the next session I will start with that script and just explain it a little bit in more detail. But let us quickly go through this solution of a symmetric potential. So this will be symmetric because it is same from 0 to minus a by 2 and 0 to a by 2. Then we have this time independent Schrodinger equation. So for the bound, and we have our boundary condition such that x for x greater than a by 2 it is 0. For our wave function is 0. For x less than minus a by 2 our wave function is 0, and for and at x equals to plus minus a by 2 our wave function is 0. Now so we can see that for mod of x less than a by 2, then only our wave function exists. So we can write our time independent Schrodinger equation, and our Vx is equals to 0 for that range. Then we can simply write we can write it like this, and we can write d square psi by dx square equals to minus k square times psi x, where k is under root 2me by h phi square. Then we can take the trial solution to be either e to the power iota kx or e to the power minus iota kx. Sorry about that. So okay, so you can check it out. You can check it e to the power iota kx and e to the power minus iota kx. Both satisfy this our TIC equation, and so we can write a general equation as psi x equals to a times e to the power iota kx plus b times e to the power minus iota kx. Now for specific solution we will use the boundary condition that at psi a by 2 it will be our wave function will be 0, and that gives us this condition a equals to minus b to the power minus iota k, and at psi minus a by 2 equals to 0 we will get a equals to minus b to the power iota k. Alright, and using dividing 1 by 2, and we will get our solution as this. What we will get is e to the power 2 iota k, that has to be equal to 1, and then from there we can get that so it means that k has to be equal to n pi by a. Alright, for n belongs to integers, and thus our energy En value, which is h square k square by 2m, it will be equals to h square n square pi square by 2m square. So our En value will be equals to n square pi square square by 2m square for n belongs to integer. Now here n could not be equals to 0, because you can see that if n is equals to 0, then what will happen for n equals to 0? Here we can see that for n equals to 0 our k will be 0, and if k is equals to, because k is equals to n pi by a, if k is 0 then a is equals to minus b. And here in our general solution you can see that it is a e to the power iota k which will be 0, so it will be a plus b, and b is minus a, so a minus a will be 0. So for n equals to 0 we will have no wave function, so n equals to 0 could not be part of our solution. Okay, so psi x equals to 0 for n should not be equal to 0, psi x equals to 0 is not possible. because it is not possible for n equals, because this will be for n equals to 0. We will have psi x equals to 0, which is not possible for mod of x less than a by 2. The particle must exist somewhere. It has to exist somewhere. Okay, now from 2, from this 2, a equals to minus b to power iota ka, and then we can put the value of k as n pi by a. It will be minus b to power iota n pi, and then we can open this e to power iota k as cos n pi plus iota sin n pi. And from here we have this a is equals to minus b for even n and b for odd n. So using this, if we put psi x equals to this, and again we will use e to power iota k is equals to cos kx plus iota sin kx, then we will get this psi x equals to phi of x equals to this for even n and for odd n. So basically, as we have proved as well, like for an even potential, our wave function we will get either even solution or odd solution. So that is what we are getting in this case. If our particle in a box problem that we have that you guys have had already solved in week 1 and week 2 as well, you have seen the solutions. So if it is symmetric potential, then also we will get this even solution and odd solution for some solution even and odd. And if you and using this normalization condition for even n, we can do the normalization condition, and then we can find our a, which and when we will find a, then we have to take into so our mod of a square for even n, we will do solution for both even and odd n. For even n, our mod a square comes as minus 1 by 2, and what we have to do is we have to use our a as such that our solution, so our for even n, our solution 2 iota a times some sin pi n pi x by a, and we want our solutions to be real, our wave function has to be real. So we will choose a such that our solution is real. So we will choose a as minus iota by under root 2 by a, which satisfies this mod a square condition as well, which we get from normalization. Then we will again do the same normalization for odd n, and what we will get, and we will again we will get mod a is equals to 1 by under root 2 by a. So we will use a is equals to 1 by under root of 2 by a. We get mod of a square is equals to 1 by 2a. Okay, let me just use minus 1. It is minus 1 by 2a. Alright, so from there we will get our psi. So using the normalization condition, we will get our psi x, and considering the a, which gives us the real wave function, real solution, we will get our psi x for even as same under root 2 by sin n pi x by a, and for odd n, now it will be under root 2 by cos n pi x by a, and the energy eigen values, they comes the same. So basically, what we have seen here is that because of the symmetry potential, the numerically the solution has changed. But what we will see next is that using our Python script, is that the physics remains the same, even though mathematics has changed. Now we have even an odd solution, but the physics is not going to change. And then also similar to our previous case, we will also take a time evolution, so equation of 2 energy eigenstate, which we can write it like this. Okay, because we know psi 1 psi 2, then we can just write it as linear combination of this, and then what we have done today in several questions, we can do this c1 psi 1 x e to the minus iota even t by h cross, and this and we will have c2 psi 2 x e to the minus iota e to h cross if our psi x, 0 wave function will be written as a linear combination of psi 1 x and psi 2 x. Alright, and this is also we have proved. A summation of c square will be 1, so mod of c1 square plus mod of c2 square equals to 1. And if we and as we have done in problem number 2, this probability distribution function will come like this, okay, with a cosine function. Alright, so we are going to use these things. So because of time constraint again, this is the solution for our infinite square wave symmetry potential. Because of time constraint, I don't think we can now. We are already over 2 hours. So in the next tutorial, in the next session, we will go through this Python script for this symmetric potential, where we will see that even though the numerically the solution is different compared to what we got for the particle in a box, the physics is going to be the same. Alright, and here also you can see that even the eigenvalues are not changing, the energy eigenvalues are same. So that also gives you an idea that the physics is going to be the same. Alright, so Okay, let me just stop sharing. Right. And let me just pin this. Just pin this. All right. So in today's session, what we did was we first completed our what was remaining in our week one, the problem number 5 of the Drude's on Drude's model from Ashcroft and Mermin. So we completed that problem. We have completed part A and B in week one, and in today's session, we have completed the remaining C, D, and E part. Then we did some problems on the stationary states from Griffith's Introduction to Quantum Mechanics, problem number 2 to problem number 4, 2, 3 and 4. Then we did problem number 5 and 6, which were on the infinite square well. Alright, and after that, because of time, and then we see the solution for the infinite square well in case of a symmetric potential, where when our infinite square well is from minus a by 2 to a by 2, so it is now a symmetric potential. And what we saw is that the solution, the numerically, that we have two kinds of solution. We have even solution, we have odd solution that we expect from a symmetric potential, although the eigenenergy values were same. So that that provides us the hint, that tells us that the physics is going to be the same. Even though the mathematics is different, the physics is still going to be the same, because it is still our infinite particle in a box problem only. Alright, because of time constraint, I couldn't go into the Python script of this infinite square well symmetric potential, and also I couldn't go through some of the two more questions that I had for this infinite square well. So in the next session, I will start with the Python script of this infinite square well, and then maybe also do one or just two more questions on infinite square well, and then continue with the topics of the next week. Alright, thank you.